This is the last of 4 lectures concerning a classical description of the electron. This lecture is of mathematical content because we are going to introduce the dynamical equations of the 2 characteristic points of the spinning electron. Dynamical equations for the center of mass and the center of charge. These are ordinary differential equations which are obtained through the general formalism which describes these objects. Well, let us start first with the analysis of the dynamical equations of the point electron. The point electron has a mechanical property called mass and an electric property called the charge, electric charge. Both are localized at a single point R. This is the main feature of the point particle. The center of mass and the center of charge are the same point. And the mechanical properties are energy and linear momentum, which are written in this form in terms of the center of mass velocity, where gamma of v is this relativistic factor. These 2 observables are not independent. They satisfy this quadratic equation. And the dynamical equations of the point electron is this. The external force is the time derivative of the linear momentum, where the external force in the electromagnetic case is this. The electric field defined at time t at the position of the charge, times the velocity of the point, which is the same as the velocity of the charge, times cross the magnetic field defined at that time and that position. If we take here the time derivative of this expression and separate on the right-hand side the highest order derivative of the position of the point, we get the second order differential equation. To produce numerical integration, where the external fields are complicated, it is better to transform this system in terms of first-order differential equations. Now we see some feature which is interesting. If in this expression electric field vanishes because the particle is only moving in some external magnetic field, the only remaining term is this, which is orthogonal to the velocity of the charge. So the scalar product of this equation vanishes, and therefore the absolute value of the velocity of the point particle remains constant along all the trajectory. Because if v is constant, energy is always constant, and the absolute value of the linear momentum is constant. So there is no energy transfer from a magnetic field to a spinless point particle. Now, let us analyze what happens to the spinning particle. You see, the spinning particle has 2 centers, the center of mass and the center of charge. Now, this dotted line tries to represent something of the shape or size of the electron, but the formalism does not describe that. The formalism is only interested in the description of these 2 points. Now, what we have here is O represents the origin of our Cartesian frame, and according to our frame, Q is the location of the center of mass, R is the location of the center of charge, and F, capital F, represents the external electromagnetic force defined at the charge position. You know, angular momentum is always a mechanical property which is defined with respect to some fixed point, some specific point. Okay, in this picture we have 3 different points: the origin of our frame, the center of mass, and the center of charge. So the angular momentum of the electron with respect to my origin, I call the total angular momentum J. But the angular momentum of the electron with respect to the center of mass, I call it spin Cm, spin with respect to the center of mass. And the angular momentum of the electron with respect to the center of charge, I call just S, the center of charge spin. Of course, these 3 angular momenta are not independent, and they satisfy the relation. So the total angular momentum can also be written as the spin with respect to the center of charge plus the cross product of r cross the linear momentum of the electron in this frame. Or alternatively, as the spin with respect to the center of mass plus q cross the linear momentum. And we can use these equations to establish the relationship between both spins. Okay, these three angular momenta are different objects, and they also satisfy a different dynamical equation. Under this external force, the torque of this force is the time derivative, the torque of this force with respect to the origin, is the time derivative of the total angular momentum. Okay, the same thing happens with the center of mass spin. The torque of external force with respect to this point is the time derivative of the center of mass spin. But the dynamics of the center of charge spin has nothing to do with the external force. This equation is independent of whether the electron is free or not. But if the electron is free, F is 0, this is 0, and this is 0, so J and SCM are conserved. For a free electron, the center of mass spin is a constant vector. It is pointing in the same direction. It's not modified through this free motion. But the center of charge spin satisfies this equation. If the motion is free, p is constant, so the center of mass is moving at a constant velocity. This is a plane orthogonal to the linear momentum, and the time derivative of this spin is moving in an orthogonal plane, so it is moving in some kind of orthogonal plane to the linear momentum. So what is conserved is its projection on the linear momentum. Now we have these features which I will show you how they behave in some numerical computation a little bit later. Now the spinning electron, these are their kinematical variables, the center of mass position and velocity, and the center of charge position and velocity. Okay, and the dynamical and the mechanical properties of this object are, as before, the inertial linear momentum, which are written in the same form as in the point particle case in terms of the center of mass velocity. But in addition to these mechanical properties, we have also the other mechanical properties, the center of charge spin, which is written in this form, and the center of mass spin, which is written in this form. Here only the center of charge velocity appears, and here the differences between both velocities. This structure is obtained through the general formalism when analyzing the invariance of rotations of the dynamical equations of the spinning electron. Okay, as before, H and P are not independent, and they satisfy the same second degree equation, this quadratic equation, as in the case of the point particle case. But in addition to this, these three objects, H, P, and S, are also not independent observables. They satisfy this equation. But this is a first order equation between H and P, and also on S. When we quantize this model, H will be replaced by the time derivative operator, P by the gradient operator, so that in the quantum case, this relationship, acting on a wave function of the electron, will produce a first-order partial differential equation system. In fact, that equation will be exactly Dirac's equation. So the model we have introduced here with two centers satisfies Dirac's equation when quantized. This is one of the most important properties to analyze its dynamical behavior from the classical point of view. Okay. The dynamical equations of the spinning electron are, as before, the external force is the time derivative of the linear momentum, but now the external force has the same structure but the fields are not defined at the center of mass position. They are defined at the center of charge position, and it is the velocity of the charge which appears in the magnetic term. And this second equation represents the relative motion of the center of charge around the center of mass. Now, as before, if I take the time derivative and put on the left-hand side the lowest order derivatives to produce first order differential equations, what we obtain are these. This is a system of 12 ordinary differential equations for the 12 variables q, v, r, and u. The only difference is that this v is always below c. However, this u is always c. And that this is always c is easily seen because if the absolute value of u is constant, it satisfies this equation. As taking this scalar product with u, we get this. The internal motion of the center of charge around the center of mass for any arbitrary observer is always orthogonal to the direction between these 2 points. So, and the acceleration of the center of charge is towards the center of mass. Even more, this last equation can help us to define in any inertial observer the definition of the center of mass position in terms of the location of the center of charge and the acceleration of the center of charge, and this invariant coefficient. Okay. Well, we have differential equations for the point particle, and we have differential equations for the spinning particle. Under an external magnetic field, as before, if the electric field vanishes, this scalar product takes this form, but now u is not v, so this is not 0. This means that the absolute value of the center of mass velocity is not constant. If it is not constant, there is an energy transfer from the magnetic field to the spinning model. Well, why? The reason is clear. The spinning model has magnetic moment, and as we see, the magnetic moment is related to the center of charge spin. And as we'll see, the center of charge spin, and therefore the magnetic moment, is oscillating very rapidly when moving the electron. So this motion of the magnetic moment in the external fields produces an energy transfer between the particle and the magnetic field. Okay, so the center of mass of the electron is not moving at a constant velocity like in the point particle. Here, in this kind of equations, you see this model has a natural unit of velocity, c, the center of charge velocity, a natural unit of length, the length between the separation of these 2 points, for instance, in the center of mass frame, and therefore a unit of time, which is this quotient, so that all variables for these dynamical equations, position, velocity, accelerations, time, and so on, are dimensionless variables. We can write always the differential equations of our system in terms of dimensionless variables. So we analyze the electron-electron interaction. All variables are dimensionless, and the only relevant physical constant, you say the coupling constant between them, is just the fine structure constant alpha, which is defined in this way. So the fine structure constant contains three fundamental constants which are related to this model. E is the charge of the particle, h bar represents the angular momentum of the particle, is h bar over 2, and c is the center of charge velocity. This is independent of the mass of the particle. So all leptons, which interact only electromagnetically or weakly, electroweak interaction, have the same attributes. So all these analyses we are going we are making for the electron is also valid for muons and the tau particle. Okay. Let us see how is the motion in a uniform magnetic field. Let us start first with the point particle. In a uniform magnetic field, the point particle, this problem can be solved analytically, but we are going to show you here numerically the differential equations. In this screen, we have the center of mass motion. This is the external uniform magnetic field along z-axis. We shall send the particle along the y-axis. In this lower part, I represent the time variation of the energy and linear momentum when the particle is moving. So the motion, what we see is this. You see, energy and linear momentum have a constant value all the time. And this is a circle. The particle describes a cyclotronic motion at a constant velocity. Stop integration and go back to analyze now the spinning particle. For the spinning particle, we have to describe also the dynamics of a spin. In this computer program, we have several windows. In this window, I will show you the center of charge and center of mass motion with the same magnetic field, the same linear momentum in this direction. In this screen, I will show you the center of charge spin evolution. Here I will show you how the endpoint of the spin moves, but also on the XY plane I show the projection of that point to have some three-dimensional idea. And the same thing with the center of mass spin, which has been selected as initial position with 30 degrees with the z-axis. And in the lower part, in this, I will show you the variation of the energy and the absolute value of the linear momentum. So let us start. I stop for a moment the integration to show what is here. The center of charge and center of mass motion is here, so the linear momentum has this direction, and the center of charge spin is moving, this is the projection, is moving in an orthogonal plane to the linear momentum. The linear momentum is changing, so this plane is changing in this way. However, the center of mass spin is like a kind of precession in this other direction. Let us continue the integration. This is always moving in a plane orthogonal to the linear momentum, you see. And here, energy and absolute value of linear momentum are not constant as predicted by the previous dynamical equations. So, when the center of charge is producing some kind of cyclotronic motion, the average value of the center of mass position describes a circle, and when I finish this turn, I will stop the integration. Okay, so this is the center of charge moving around the center of mass motion, but what we see is the cyclotronic motion has an angular velocity along the direction of the magnetic field. However, the center of mass spin is precessing backwards. We have the angular velocity and in the opposite direction. This is the dynamics of both spins. The average position up to a turn of the center of charge position, if I compute that, is this. So the center of mass spin is a kind of average value of center of charge spin. But the center of charge spin is Dirac's spin. In the quantum mechanical description of the electron, Dirac's spin is written as a 4 times 4 matrix, h bar over 2. These are 2 by 2 sigma Pauli matrices. And this spin satisfies, even with interaction, this dynamical equation, where P is the linear momentum, in Dirac's theory is the gradient operator, and U is Dirac's velocity operator written as C times Dirac's alpha matrices. Alpha matrices do not commute. This means that the three components of the velocity operator cannot be measured exactly with simultaneity. But if I am able to measure one of these components, because the eigenvalues of alpha matrices are plus or minus 1, the velocity of this point, which is moving at this velocity, is plus or minus c. U is the velocity of the point r of which Dirac's spinor depends on. So Dirac's spinor is expressed in terms of the position of a point moving at the speed c. So it is clear that in Dirac's theory, Dirac's spin represents the spin with respect to the center of charge. Not only satisfies the same dynamical equation, but it is described in terms of the velocity of a point moving at the speed c. Okay, these dynamical equations were published in this Journal of Physics A, and people interested can get these 2 documents of a lecture course I lecture at the University of Basque Country. You can contact me, and all the above numerical integrations have been performed with this dynamic solver numerical computation program. And with this, we finish this set of 4 lectures concerning the classical description of the electron. It is possible to have a classical description of a spin which has very nice features which are also obtained through the quantum mechanical analysis of Dirac equation. Thank you very much for your attention.